I posted for you the solution for all of these problems. So as I told you during live sessions, will not be able to do all of them, but I will tackle new ideas with you. Okay? So for example, there is a new concept that needs some analysis that I will go over in some problems. This is why I will start with the following problem. We have a hydrostatic force F is the same on the bottom of all three containers, even though the weights of liquid above are quite different. The three bottom shapes and the fluids are the same. This is called the hydrostatic paradox. Explain why it is true and sketch a free body of each of the liquid columns. So what we will do here, we will demonstrate together that even if I have different volumes, maybe at a first sight, you might say, because I have different volumes of fluids above the surface, I'll have a different force on the surface for the three containers. This is wrong, we will see why, okay? This is why I told you, when I do some derivations, it is very good to understand the concept, because you might need it in something else. And this is an example. To understand here why the three forces are equivalent, first, if we do some analysis, this force is due to what? This force is due to the pressure force of the fluid on the bottom area, okay? What is common between the three bottom areas is that it's the same area. So A is equal for all. This is a first common factor. The second common factor between the three containers is that the depth of liquid in the container is the same. So for the three containers, the depth is H and it's common. So if you just look at this figure and you say F is due to what? F is due to the pressure forces acting on this area. And you know that since I have a fluid that is static, everywhere in my area, since I move in the horizontal plane, I will have the same pressure, which is equal to gamma of the fluid times the height h. And of course, I have here atmospherical pressure, I can add it, but I can consider that it is negligible compared to pressure exerted by the fluid. So for the three containers, okay, the pressure force is the same. The pressure is the same. And since I want to calculate the force, since it's a constant pressure, the force is simply equal to the pressure times the area. So the total force acting on the bottom for the three containers is gamma times H times A. Now, how can I physically explain how different volumes of liquid will lead, so different weights will lead to the same force acting on the bottom? This will require some analysis. If you remember, when we are interested into the interaction force between a fluid and a surface, what was the strategy? The strategy was to consider a control volume of the fluid and put all forces acting on it. So if I'm working on this shape here, okay, if I'm working on this shape, what are the different forces acting on this system? I will draw it, and I will put forces acting on it. So first, the first force is the weight. So I should consider the weight of the fluid. Okay. Now, since this is an inclined surface, you know that the total action of the surface on water will be perpendicular to the surface. Okay. And in case you want to find its exact location, you can do it using the formula of YCP and XCP. Okay, so you have a force of the inclined surface on water from both sides. Okay, here if you take a look, it seems that due to symmetry, okay, you will have the same, because it's a symmetrical container, you will have same values along the horizontal direction, and these two forces will cancel out. While in the vertical direction, you will have two components that are acting downward. And finally, you have the bottom surface. The bottom surface by action reaction. Since the fluid exerts on it a downward force, by action reaction, the bottom surface will act on the fluid by an upward force. And this upward force F is equal, as we have demonstrated together now, it's equal to gamma times H times A. Let us do a small analysis of this term. What is H times A? If you do H times A for this container, this is the height, and this is the area. If you do H times A, this is equivalent to this volume, this one. Okay? So we can replace HA by the full volume. So if I take at this level a horizontal line, and from my area I take verticals, I will get a full volume, but in reality, I have these will be called missed parts. So in reality, I don't have fluid here, but this term H times A is equivalent to this volume. And when I multiply it by gamma, this is equivalent to the weight of the full volume. Okay? So now I can replace F, if you want, by W of the total volume. And now let us write our equation to see what we will obtain. We will sum in vertical directions, since as I told you in horizontal directions, the effects will cancel out. So if I consider y-axis upward, and I do, due to static condition, sum of forces along y equals to 0. And I take the positive direction upward. Then I will have plus weight of total volume, okay, minus the weight of the actual fluid, and the fluid is filling this part, okay? So this is minus W fluid because it's downward, W total volume minus W of the filling fluid, okay, minus the weight of the filling fluid, and minus, so here we have two horizontal forces that are acting downward and they are equal due to symmetry. So minus 2F vertical, and this represents the action of the surface on water in the vertical direction, equals to 0. So what can you deduce? You can deduce, if I take this term to the other side, and I can deduce that F vertical on each part is equal to W total minus W filling fluid over 2. Let us do some analysis of this term. This term represents what? When you subtract the total volume minus the volume occupied by the fluid, you will obtain this volume of fluid. So on this surface, since it's over 2, on this surface, you will have the action of this weight. If it was, and it's like you will think as it was filled. Okay, this is why we call it missing part. So we say we can express it in the following words. When I have an inclined surface above the fluid, the action of the surface on the fluid is equivalent to the weight of fluid of the missing part. So if I consider that I have a fluid in this missing part, its weight will be the action of the surface, the vertical action of the surface on the fluid. If I didn't have symmetry here, all I have to do, I will take as control volume this part alone and do its analysis. And I will end up again with the same result, because this will be then the filling volume. The total volume will be this one. And when I subtract the whole volume minus the weight of the whole volume minus the weight of the filling volume, I will obtain the weight of the missing part. So we say, in other words, that when a surface is like this. It's not below the fluid, it's above it. In order to find its action on the fluid, I consider the weight of the fluid in the missing part. Okay? Is it clear, or do you want me to repeat? Let me check your charts. Hassan, what do you mean by average? So here you have a constant force everywhere because you have the same, look, you have the same height, you are moving in a horizontal plane, so the pressure is the same. No need to average here. I don't know if this was your question.
لا دكتور انت سألت انه الويت توتال ماينس الويت
Okay. Who will weight of the missing part? Okay. When we do the total.
انا ما انتبهت للماينس فقلت افريج يعني تسرعنا.
Michelle, do you want me to repeat from beginning or you have something specific?
Just the missing part, but can you repeat this?
Okay, look, I will repeat the procedure for this container now. Okay, so you can understand it. Here, for example, for this container, no need to do the analysis of the missing part. You know why? Because here the surface is below the fluid. So here, if you want to do the analysis here, this is an inclined surface. Okay, we have seen together that the vertical force on an inclined surface is due to the weight of fluid above it. Okay, so here you can easily say that the action of the water on the surface will be like this, and that will be divided into horizontal and vertical component, while the surface action on the fluid will be upward. Okay, so here when you want to divide, you consider this is the force of the surface in the horizontal component. This is the vertical component, and we know from previous study that when a surface is below water, then the action of water on it is equivalent to the weight of this part. So here in this container, we'll not talk about a missing part, no. While here, why we should talk about a missing part? Because we demonstrated together that this force F is due to what? Is equal to the weight of the same fluid filling the whole volume. Because here, imagine this is your area, okay? And you have a certain height h. When you write A times h, what do you get? You get this whole volume. Okay, this is called the full volume. This is the full volume, okay? While in reality, the filling volume is this one. This is the filling volume. Since you have constant depth, if you subtract the total volume minus the filling one, what do you obtain? You get these parts, this one and this one. And here, because of symmetry, forces on these two are equal in magnitude in the vertical direction. Okay. Now, I repeat, in case if it was not a symmetrical container, you take each surface separately. You do the analysis on this surface first. To be able to do the analysis on this surface, you just take a control volume limited by this surface, which is this one. And now you can repeat the analysis along this control volume. Again, in the horizontal direction, the forces will cancel out, because if you remember, when I consider a certain surface, okay, even here, if it's an inclined surface, I can still apply the concept of curved surface. So if I project it on the vertical plane, FH will cancel out the horizontal forces. And I can understand this because the pressure is not varying in a horizontal level. It's only varying along a vertical level. So now I will just have, when I consider this part, I will just have the action of this area here. So let's call it here small area, let's say A prime. And this is the height. This is the height H. Okay. So now if I consider this part only, this control volume, the downward force, the force between the surface and water. So since water is acting as a downward force by action reaction, the area A prime will act on water upward. And the value of the force from the bottom surface on water will be equal to the pressure on A prime, which is constant because I'm moving in a horizontal plane. time A prime. And the pressure again is gamma times H. So when you see H times A prime, this term represents for you what? If you draw it, you have an area here, let's say any area. If you multiply it by H, what do you get? You get this volume. The volume limited by the area and the height. This is called the total volume. This is the total volume, okay? While the actual liquid is filling only this part here. This is why we give the name for this part here, we call it missing part, because I don't have a fluid here. But when I did the analysis of my force terms, I obtained the weight of the full volume in case it's filled with water. Okay, because gamma times A prime, gamma times the volume, which is A prime times H, correspond to this whole volume. And when I multiply the volume by gamma of the fluid, I obtain the weight of the full volume. Okay. Now, since I have, when I draw the free body diagram for this part, since I'm considering this part, I should put as forces its own weight and the action of the bottom surface. So as you, and of course, the action of the inclined surface, which is decomposed into horizontal and vertical components. But as we said, the horizontal component will cancel out. So you just have to determine what is this force FV prime, let us call it. So to get FV prime, all you have to do is to do the balance along Y. So you will get this force we have demonstrated that is equivalent to plus W of the total volume, while this force is the actual weight of the fluid above the surface, above the bottom surface, which is minus W of the filling fluid, okay, minus FV prime equals to 0. If you take FV prime to the other side, what do you get? You get that FV prime in magnitude is the weight of the total volume. So in case, this is imaginary weight if you want. It's not, I don't have a fluid in the full part, but the expression of the force here is equivalent, is equal to the weight of the total volume. And when I subtract from it the weight of the filling part, so this is a part filled with water, so minus, or the fluid, so minus W of the filled part. When I subtract them, what do I get? So if you just subtract this whole volume, if you subtract from it this one, okay, of course you have a certain depth here, you will get this part. This is called the missing volume. Okay, so I can deduce that if I have an inclined surface and it's above the fluid, I can deduce that the action of this surface on the fluid is equivalent in the vertical direction to the weight of the missing part of the fluid. Okay. Okay. What is the paradox side? The paradox is that different weights will give us same pressure, same force on the bottom surface. This is the paradox. Because at the first sight, you might say, because here I have more fluid, so a larger weight, I expect to have a larger force on this bottom area. Why this is wrong? Why this is wrong? Because here the inclined surfaces are helping the bottom surface into sustaining water, or the opposite. So if you consider this container, the vertical action of the surface is upward. This is why the action on the bottom surface will be reduced, because these surfaces will help the bottom surface into sustaining water. And if you perform your calculation, these surfaces will just be responsible of handling this weight. This surface will handle the weight above it, while the bottom surface will only handle this weight here. In this example here, you don't have any inclined surface, so your bottom surface will handle the whole volume. because your vertical surface will only apply horizontal forces that will cancel out. They will not apply any vertical component. So this surface will just handle this weight. And finally, for this case, it's the opposite. For this case, we have demonstrated together that these surface action on the fluid are acting in this way. So their vertical component is downward. This means that they are increasing the pressure acting on the bottom surface instead of reducing it. And if you add the action of the weight plus the action of these forces, which represent the weight of the missing part, you will end up at the end to have the same F for all three cases. Because for all three cases, the force on the bottom is equivalent to the weight of this part, which is gamma times A times H. And since the three containers share the same bottom area and the same height of fluid, even if they have different shapes, they will have same force exerted by the fluid on the bottom surface. Okay. It does matter how much liquid if you want, but I should have same height. This is the condition. But yes, it doesn't matter the volume. I can have different volumes with different shapes. The only condition to have same effect, same height for all containers, and same bottom area. So you can have any shape, any profile. Your profile will not, the profile of your container will not affect the result as long as I have the same height and I have the same bottom area. Okay. Any other question on this? Okay, I know this concept is a little bit hard. This is why I will go over another problem to tell you how you can think directly about the missing volume. If you look at the following problem here, okay, let's say your purpose is to determine the forces of water on this gate. This gate is formed by two surfaces, one vertical and one horizontal. Concerning the vertical force, I don't have any problem with it because we have seen together how we calculate the action of water on an inclined surface. Just I should replace theta by 90 degrees, and I can determine what is the total force. And here it's horizontal because it's perpendicular to the surface, and I can get its point of application, YCP. And if you remember, we said that when we have a rectangle and it's just exposed to the, we have P atmospheric, okay, at the surface level. So we can neglect P0 compared to the pressure exerted by the fluid. We can demonstrate that the acting force is at H/3 from the bottom, or at, if you want, 2H/3 from the top of the from this surface here. Okay. So we are done with the horizontal force. Our challenge here is, what is the force of water on this part, on A? So whenever you have a surface above the fluid, not below it, because when the surface is below it, we have developed together that the action of a fluid on a curved surface, and you can extrapolate it here on this surface, is equal to the weight of fluid above it. So if you have this shape, your gate is below, and you have a certain height of water, you can just say that the action of water on your bottom surface is simply the volume of water above it, just above it, as we have seen in the previous problem. Here, I don't have water above the surface, I have water below. Whenever you have water below the surface, what you will do, you will say, this is my area of interest. Okay, I look at the free surface level. Where is the free surface level here? I extend it and I say, this is the missing volume. This is the missing volume of water. Okay, because here, again, if you do the analysis again, okay, you can consider No need to do the analysis each time, but I just explain it for you to know how it comes from. So you can directly here say, this is the free surface. If I had the volume filled, this is my mist part. This is my mist part. So the action of water on the surface will be equivalent in magnitude to the volume, to the weight of fluid of the missing part. Okay? And of course, since your surface is above water, water will exert on it a force that is upward. So you can just simply say here that this force, because of symmetry effect here, it's a rectangular shape, the force will act just at the middle since I have constant pressure here. Okay, I'm moving in the horizontal plane. Since my pressure is constant, the force is acting at the middle, and the value of it, okay, is equivalent to the missing volume. If I didn't pay attention for this, how I can derive it? How I can again derive this result? Always same concept. My fluid, my limiting fluid of interest in contact with AB is this fluid. Okay. If I want to do the analysis of this fluid, what do I say? I say that I have the action of AB on it, and I don't know it. I want to find it. This is FAB. And in the vertical, of course, I have the weight of this filling part, this one, W. And I have the force from the bottom level on this area, which is an area equal to AB. Okay, so if you have a certain depth, D, then your area of interest will be AB times D for both sides, here and here. Okay, because this is the control volume I will consider. So this is D, and this is in length equal to AB. So I am dealing with the same area. If you want to do the analysis on this filling fluid, and you want to write what is happening in vertical direction, as you can see here in horizontal direction, these effects will cancel out, and I will just have what is happening along the vertical line. So what do I have? I have minus FAB, which represents the force of the surface AB on the fluid. I have minus the weight, I will call it filling fluid. So this is the terminology we are using. This is the filling fluid I am considering. And I have plus this force, I will call it F of bottom surface. Okay, so plus F bottom. Let us look together. What is the expression of the force at the bottom? You know that whenever you want to find a force, okay, you can say that here water is exerting pressure on the surface. So by action reaction, okay, the action of the fluid on the surface is equal and opposite to the action of the surface on the fluid. If I am interested in the action of the fluid on the surface, as I am moving here along the horizontal level, I can say that the pressure here in these points of the area of interest are equivalent to pressures at these points, because we are at the same horizontal level. And these points are characterized by which pressure? All of these points have the pressure equivalent to the pressure of a height h of the fluid. Because look, why I didn't look at these points? Because I don't know what is the pressure here. You know why? Because the pressure here is affected by FAB, and I don't know what is FAB. My purpose is to get FAB. So I cannot know the pressure here from FAB. I need to go to another way. So I say, since I'm moving here in the horizontal level, the pressure is not changing. So I can say that pressure at these points here is equivalent to pressure at this bottom level. And since here the reservoir is exposed to atmosphere P0, so I can say I will neglect the effect of P0 compared to the pressure exerted by the fluid. And then I can simply say that the force here on the bottom level is equal to the pressure times the pressure exerted P is equal to H times what? What do I multiply H by? By rho G or gamma. Okay? And since the pressure is the same here everywhere, I can then say that F bottom on my control volume is simply the pressure P times the area of concern, okay? Which is this area here. And since the pressure, I can replace it by gamma times H. So now again, if I do the analysis of this term, H times A, what do I get? This is H, this is the whole H, and this is A. If I multiply H by A, I get this total volume. So again, F bottom here is equivalent to gamma times the total volume, which is limited by the free surface and the area of interest. So again, I will clear it again. So now, this is my total volume. If I draw it, this one. Okay. And the weight of the filling part is this one. So when you subtract the total volume, okay, the weight of the total volume minus the weight of the filling water, you will get the weight of the missing part. But instead of each time repeating this analysis, once you understand the concept, you can directly apply it. You can directly say that the action on AB is equivalent to the weight of the missing fluid. And just remember to determine the limit of the missing fluid, you go to the free surface and you draw your volume like this. Okay. Is it clear? Any question on this idea? Okay. So I encourage you now to try to do this problem. This is the same concept again. I have here a surface that is above water. So if I want to find the vertical action on it, I will draw the total volume. This is my free surface. I draw a line like this, and the volume is limited by the bottom area. So this will be my missing volume. So the vertical action will be equal to the weight of the missing volume. And for the horizontal action, it's exactly the same procedure we follow for a curved surface. So I have a curved surface. I want to find the horizontal force acting on it. Okay. Please go over the videos, and I am available for your help anytime. So if you have any problem with the explanation, just send me a WhatsApp and I will answer. Okay. So this is about this concept. Any question on it before we proceed? Okay. So now I will go back to the course material. Do you see the file of course material now?
Yes, doctor.
Okay. So now one of the main concepts also in this chapter is buoyancy effect. And I think that you are familiar a little bit from school, because in physics you have tackled buoyancy effect. Okay. So what is the idea here? The idea is that if I have a certain object that is immersed in a fluid, to know its equilibrium state, if it will move downward to the bottom, or if it will float on the free surface, or if it will remain somewhere in equilibrium in the middle of the fluid, this will depend on the balance between buoyancy and weight. Okay, you have learned at school that whenever I have an object submerged into a fluid, to consider the buoyancy force, which is the action of the fluid on the object, I just consider what is the submerged volume, and I say that the buoyancy force will be equivalent to the weight of the displaced volume. So this is the displaced volume, and it's the weight of fluid occupying the displaced volume. So I don't multiply this volume by gamma of the object to get the buoyancy force. I multiply this displaced volume by gamma of the fluid. Okay. While when the other force acting on my system is the weight. And of course, the weight will take into consideration the whole volume of my rigid body. And now I can understand how the analysis can be performed. In case gamma of the fluid is higher than gamma of the body, so to have equilibrium, what should happen, do you think? Because what are the expressions of the two forces? For weight, it's gamma of the body times total volume of the body, V total, okay? While the buoyancy force, F buoyancy, is gamma of the fluid times the immersed volume. Always an object will tend to equilibrium conditions, okay? So if you look at these two expressions, in case gamma fluid is larger than gamma of your body, what will happen? Since in equilibrium conditions, these two will be equal. So W and buoyancy force will be equal, okay? So what will happen is that to reach equilibrium condition, since this term is larger than gamma body, the immersed volume will tend to be lower because I will reduce the immersed volume until reaching the condition that gamma body times V total equals gamma fluid times immersed volume. So when gamma fluid is larger than gamma body, the equilibrium condition will be by having floating of the object, because in this way, by reducing this submerged volume, I can reach an equilibrium state where gamma fluid times volume immersed or submerged is equal to gamma body times the total volume. Okay. On the other hand, if